Hi everyone. Um, in this video we're going to be moving on a little bit from what we've been doing in class and taking all of our probability, a step uh, further. So what I'd like to do now is, let's see, I would like to just start out with a reminder that the probability of any event is equal to the total number of successes over the total possible outcomes. And what we're really going to be focusing on today is this denominator here. How do we figure out those total possible outcomes? So in class, we've been looking a lot at M&Ms. So for example, let's imagine that we pull out one M&M of each color, a red, an orange, a yellow, a green, a blue, and a brown, just like we were doing in class today. We're going to put those in our cup, right? Here's our sort of cup here. And they're all mixed around in there, and you're going to stick your hand in there and pull one out. I'm not much of an artist. Okay. So keeping it really simple, let's start with the probability of drawing a red M&M is the number of successes. Well, how many red M&Ms are in here? There's one. There's one success over how many total possible outcomes. I can reach my hand in here, and there's 1, 2, 3, 4, 5, 6 different M&Ms I could potentially get. So here's that bottom number, 1, 6. Okay, and then if you recall, if we put that M&M back in and we do that twice, what's the probability of putting your hand in and getting the red M&M, then throwing it back in the cup, mixing it up and doing it again? Well, that's the multiplication rule. So, but it's this same formula again. One red M&M, one success out of 6 possible M&Ms in the cup. Put it back in, so the same thing happens again. There's one red M&M in there and 6 possible M&Ms to choose from. We multiply those, becomes 136. All right. So what I want you to think about now is this really, let's really focus on this number down here, this 36. What I want you to think about is instead of putting that as total possible outcomes, let's think of that as how many ways can I get 2 candies? Okay, how many ways can I do it? Because that's really what this bottom number is. It's all the possible outcomes. So the question is, how many outcomes are there? Well, what I want you to do is think about, we're going to just think about just the denominator here. And so if we think about that, I can ask myself how many candies are in the cup. There's 6. So there's 6 choices for my first time sticking my hand in the cup, right? And then I'm going to throw that candy back in. I'm going to stick my hand in again. So now I've got another 6 possible outcomes, right? 6 times 6 is 36. And this is what we call a counting principle. It's the way we count things that can happen, and then they get multiplied. All right. What happens when we don't replace that candy? Let's think about that. Let's say, how many ways can I get 2 candies without putting it back? Without putting it back. So if you think about that, I can stick my hand. I've got 6 choices for the first one times, and now I'm going to stick my hand. And now I'm going to leave that first candy out. I'm going to take one out and I'm going to put it over here, and then I'm going to go put my hand back in and take another one. How many choices do I have now? There's only 5 candies left, only 5 choices. So now I have 30 possible ways I can get 2 candies when I don't replace it. So how does that tie into to probability? Well, let's think about the probability of getting a red candy and an orange candy. Okay. Well, if we first do it with replacement, it was that same thing. It was the one like up here. It was just up here where you replace the candy, right? So but I also have to consider all the different ways it can happen. So I could reach in, get the red candy first, and then the second time get the orange. Or I could get the orange candy first and then the red, all right? So these are my successes. Now I'm thinking about the top number, but the bottom number is going to still be that 36, and you'll see why, because this first event, the probability of getting that red one is 1/6 times the 1/6 plus the same thing again, 1/6 times 1/6. So we end up with 136 plus 136. All right, and so that becomes 2 out of 36. So if we break that up, if I really want you to think about what that means, it means that the bottom number is 36 because I was replacing it just like I got up here, just like I did from the counting number. There's 36 ways to draw two candies. There's just 36 different ways that I can put my hand in and take out two candies. Okay, of those 36 ways, this numerator right here, becomes all the different ways that you can arrange these two letters here. So I can arrange them. If we think of this as an arrangement, I could range it as red then orange. I can range it as orange then red. Okay, this then reduces down to 1/18th, and that is why the chances of pulling out two different colored candies is actually a higher percentage than pulling out two candies that are the same color twice. All right. What happens if I don't replace that candy? Okay, what's the probability of getting an orange and a red if I don't replace that candy? Well, it's going to be the same thing again. How many ways can I pull out two candies from this set of 6 if I don't replace one? Well, the bottom number is that 6, right? And the second time is 5 because I'm not putting them back. And then, so that's going to work out to be 30. Right? And in the numerator, I've got this, well, this is going to be 1/6 and 1/5, but we're going to have to do it twice because, again, we've got these two different arrangements. So there's two actual successes. These are your successes. This is your numerator. And this is your denominator. These are all the ways you can get those. You can choose two candies, and these are the two ways that you can get what you want. So 2 out of 30 is 1/15. Okay. So we're just kind of thinking now about what's happening in the denominator and what's happening in the numerator. And these are all part of what we call counting principles. And this becomes very useful as our numbers get much, much higher. Okay, let's do another one now, one more, where we add another candy. What is the probability now of getting a red and an orange and a yellow? We're going to draw 3 candies this time, and we're not going to replace them. We're going to stick our hand in that cup, and we're going to pull out 3 candies. What's the probability that we grab the red one, the orange one, and the yellow one? All right, so let's try to do this now in terms of what's going on up here. So let's start here with the number of successes. Remember, the number of successes were all the different ways that you can arrange these 3, right? So we can do, we could draw the red one first, then the orange one, then the yellow one, or we could get the red one first, the yellow one second, or the orange one. And you could keep listing those all out, and what you will discover is there are 6 different ways, 6 ways that you can arrange those 3. Okay? And really what that is it's like saying for the first spot, for this first candy that you pick, you've got 3 choices. Once you've picked one, there's 2 left, and so you've got 2 choices for the second candy that you pick. And then for the last candy, you only have the 1 choice, whatever's left there. So that is 3 times 2 times 1, and voila, it equals 6. So you don't actually have to go through the process of listing all the different ways. It just is this, it's always going to be this what we call factorial. And the way we denote that is we would say there's 3 factorial ways of arranging these 3 colors. And all that exclamation point means is 3 times 2 times 1, everything below 3. And that equals 6. So 6 is our numerator. That's all the ways we can get the success. All the ways we can get these 3. Okay, what about the bottom? All the possible outcomes. All right, well now we're up here with the 6. How many ways can we get 3 candies from the 6? Right? We're going to stick our hand in 3 times and pull out 3 candies. How many different things can happen? We know there's 3 ways we can get a red, an orange, and the yellow. The question, though, is the denominator is what are the total possible outcomes? All right, well, let's use that same thing again. We are going to choose 3 candies. How many candies do we have to choose from? Well, we have 1, 2, 3, 4, 5, 6. So when we reach in, there's 6 possible candies we could choose. 6 possible candies we could choose. After we've chosen 1, there's only 5 candies remaining. We have 5 choices left. And after that, we're only going to choose 1 more candy, but there's still 4 candies in the cup, so we have 4 candies there. All right? And if you do that on your calculator, you're going to discover that that is 120. We don't go all the way down times the 3, 2, 2, 1. So this is not 6 factorial. 6 factorial would 6 times 5 times 4 times 3 times 2 times 1. But we only want these first 3, 6 times 5 times 4. Right? And there's a way we can do that, and I'll get to that in a minute. But right now I'm just going to go ahead and I'm going to put this 120 over here. Okay. And that's how we can do this a little faster than trying to actually list every single probability of red, then orange, then yellow, plus the probability of red, then yellow, then orange, plus the probability, and then multiplying each time 1/6 times 1/5 times 1/4, because it's going to be the same every time. So what you're doing is you're doing it 6 times 1 over 120 for each of them. Okay, and that's how that works out. And then if you go to your calculator, you can simplify that to 1 over 20. So there's a 1 in 20 chance that if you stick your hand in and pull out 3 candies, 1 in 20 chance you'll get the red one, the orange one, and the yellow one. Okay, because we don't actually care about the order. We just have to take the order into consideration. All right, so what does this all mean? And this is really cool stuff, because what happens is you can start getting to numbers that are really, really big, and you have this method that saves you a lot of time. So let's just quickly imagine here. Let me take another color. What if we said, what's the probability of 4 colors? Think about that. What is the probability of reaching in and taking out 4 candies? Well, let's say I want the red one, the orange one, the yellow one, the green one, and the blue one. 1, 2, 3, 4, 5. Sorry, I just did 5 and then 4. We can do 5. All right, same idea. Try it. See what you get. Well, let's start with the numerator. How many different ways can I arrange these 5? That's going to be the 5 factorial, right? There's 5 factorial ways I can arrange these, all of which will be success, out of how many different ways can I choose 5 candies? How many different ways can I choose 5 candies out of a set of 6? So the bottom number goes up here. Bottom number goes up here and says, okay, well, I've got 6 candies, but I'm only choosing 5. 5, so we've got the 6 choices for the first one, 5, 4, 3, and 2. Actually, that is 6 factorial, because 1 wouldn't really matter. So you end up with 5 factorial over 6 factorial. But we'll come back to some other problems like this. But as you can see, it doesn't matter how many numbers we get now. We could go back to our whole cup of 122 candies if we wanted to. All right, let's try a couple other things. What I want you guys to think about now is like your cell phones, right? I'm imagining many of you have a cell phone, and my question is for you: do you have a PIN code every time you open up your phone? Does it, after it locks out, do you have to punch in a code? And some of you may have a 4-digit code, and some of you may have a 6-digit code. And why would you pick one over the other? Well, let's say somebody steals your phone, okay, and they're trying to break into it. What is the probability that that person will guess your PIN code. What is the probability of that happening? What's the probability of somebody guessing your PIN code? Okay, well, we're always coming back to our wonderful formula. So we can start with the total possible outcomes. Let's start with the denominator. How many different possible 4-digit PIN codes are there? Well, that begs the question of whether or not you can use digits twice. Let's start out with saying you can. You can have the same digit, like your PIN code could be 5528. So you can pick the same number twice. All right. So my question is then, how many different ways can you get those that 4-digit PIN code? Well, the first question is, how many digits do we have? Well, we have 0, 1, 2, all the way down to 9. So we have 10 actual digits that we can choose from. So for our first digit, we have 10 choices. We have 10 digits that we can choose from. Times, again, the second digit, we have 10 choices because we can use the same number twice. The third digit is 10 and the fourth digit is 10. So this turns out to be what we would say 10 to the fourth power. 10 to the fourth power, which means 10 times 10 times 10 times 10. You can do that on your calculator. There's usually like a little caret button. Or you can multiply 10 times itself 4 times, but you will get 1, 2, 3, 4. So you will get 10,000 there. 10,000 different PIN codes that you could potentially choose with a 4-digit PIN code. So what is the probability somebody guesses your PIN code? Well, how many PIN codes do you have? How many successes are there? There's only one. One out of 10,000. So think about why they recommend so much that you do a 6-digit PIN code. Why would that make a difference? Because if you had 6 digits instead of 5, look what happens. Now you're going to choose a 6-digit PIN code. By doing that, you get 2 more 10s that you're going to multiply by. So instead of 10 to the 4th outcomes, you've got 10 to the 6th outcomes, which is going to equal, instead of 10,000, it's going to equal 1 million. 1 in 1 million chance now of guessing your PIN code correctly. And that's why this is much more secure. So if you still have a 4-digit PIN code, you might want to think about changing it to a 6-digit. Right? So we're still always coming back to this formula. It's just figuring out these possible total outcomes starts to get a little more complicated. So the other possibility, and let's do another color here. Let me go to yellow. What is the possibility of guessing your PIN code? Guessing the PIN code again, if you can't use repeated digits. All right, you can't use repeated digits. So we'll do the 4 again. 1, 2, 3, 4. But you cannot use the same digit twice. All right, so that's going to change things a little bit. Now instead of having the same number and 10 to a certain power, we only have 10 choices for that first slot. Because whatever number we put there, let's say we use the 5, then we can't use the 5 again. So now we only have 9 choices for our second number. And then we only have 8 choices for our third number, and 7 choices for our last number. All right. And so this we can do on our calculator, 10 times 9 times 8 times 7. And you will get a rather large number of 5,040. Oops. 5,040. Okay. But again, the number of successes, the numerator, how many pins do you have? Only one. All right. So try it with a 6-digit pin code. See what happens then. All right. Okay, so what's going on here? Let me give you a couple of rules. Okay, so these are the 4 different counting principles that we're going to look at. And we've actually done most of them in one way or another. So this this first one here, let's take a look at that. Let's imagine this 4-digit PIN code. And if you remember from the last screen, if you could choose the same number twice, you could arrange those 4 digits, 10, 10 to the 4th power, right? There were 10 possible numbers to choose from. That's the n. And 4 was the number of digits you were going to choose. So this was like the 10 times the 10 times the 10 times the 10, 10 to the 4th power. Okay. So I could ask you, how many different ways could you do a 100-digit PIN code? 100-digit PIN code. Oh my gosh, if you had to actually list them, that would take you a lifetime. But really, what is it? You've got 10 numbers to choose from, and you want 100 digits, so that's going to be 10 to the 100, and that's going to be a number too big to even write down. But you get the idea. So this is one thing that can happen when we have repeats. Okay, what if the next thing we did is actually this one over here. It's called a permutation. And this was the one where you couldn't repeat the digits. So we had 10 for the first choice, then 9 for the second one, 8 for the third, and 7 for the fourth. It's really kind of simple mathematics. And we ended up with 5040. Okay. Well, what did we really do here? It's what we call a permutation. We had, n is still that 10. We had, so in this case, n is equal to 10 because we have 10 digits we can choose from. 0, 1, 2, all the way up through 9. We have 10 single digits we can choose from. So for n is going to be 10. So this is what we would say 10. And then we need to permutate or arrange them. But not all 10 numbers, just 4 of them. How many different ways can we start out with 10 digits and can we arrange 4 of them? All right. And I will show you in class, but you will notice on your calculator that if you type in the number 10, then you click the NPR button, and then you type in the number 4, and if you hit equal, it's 5040, right? So you don't actually have to go through this process, because then if we're back to that 100 things, that becomes tough. How many ways can I choose a 100-digit PIN if I can't repeat? Well, that's not possible. I take that back. You can't do that because you'd run out of digits. Bad example. Come up with another one. All right. So these are the 2 things we've looked at so far: just an exponent and a permutation. Okay, so that means, what is this one here? What is this n factorial? Well, n factorial is just very much like this permutation, only you're arranging all the numbers. So in other words, what if I was going to do a 10-digit code? 10-digit code, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means, and I've only got 10 digits to choose from, so really the question is, how many ways can I arrange these 10 digits? And I can arrange them 10 factorial ways, which is the 10 times 9 times 8 times 7 times 6 times 5. I'm not going to write it all out. But again, there is a factorial button on your calculator. All right. So these 2 are very much related. The only difference is you use the permutation when you're not arranging all the numbers that are given. You're only arranging a certain subset, like 4 of them or 6 of them, depending upon, so you're choosing 6 and then you're arranging them. Okay. All right. So what is this last one? This one is very important. I'll take a new screen to talk about that one. Okay, if you recall in an earlier screen when we were talking about pulling 3 M&Ms out of the set of 6, and I asked you that what's the probability of getting the red one, the orange one, and the yellow one, and we worked that all out. We ended up with 6 over 120, and if you remember correctly, 6 was the 3 factorial, the ways we can arrange all 3 of these letters, over the 120, which was the way we could permutate. We had um, six candies to choose from, and we could arrange them, and we were going to take out three, and so we're arranging three of them. And if you do that on your calculator, you will discover that 3 factorial is 6, and 6p3 is in fact 120. Okay, so, but then what happens? When we reduce that down, we end up with actually 1 over 20. So what is the difference between this and this? It has to do with those arrangements. It has to do with those arrangements. So the arrangements are here on the numerator, and then they're over here in the denominator. So we're dividing through by the arrangements. So this is where we come up with combinations. Combinations is a special formula where the order doesn't matter. It doesn't take into account the order. The formula comes from right here where you divide through by those numbers of arrangements. These are your arrangements because that was your 3. These are the r factorial. These are the three things that you were arranging, and this is the whole big 6. So this is the 6 factorial. So this is where this comes from. There's a button on your calculator. I don't want you to worry too much about this formula, but it allows you to go straight to this here when order does not matter. So try it on your calculator. If you do 6 permutate 3, you will get 120. That means there's 120 ways to arrange 3 candies out of a set of 6, or 3 of anything out of a set of 6. But if you do 6C3, or I like to think of the word choose, just choosing, not arranging, there's only 20 ways to choose the 3 candies, because you choose the red and the orange and the yellow once, and you're dividing through by all the arrangements. You don't worry about it. There's only actually one way to get a red, orange, and yellow. The red, orange, and yellow. It doesn't matter the order. So in other words, order matters with permutations. Order matters. With combinations or choosing, order does not matter. Okay? So let's just try a few questions where we apply each of these.